So in the last video, we looked at the comparison test, and the comparison test was nice. It allowed us to compare a series AN to a secondary series Bn, as long as we were able to get the inequalities in the right direction. There was a bit of, sort of a finickiness to it, in that if Bn was convergent, then we needed Bn to be larger than or equal to An, and if Bn was divergent, then we needed Bn to be smaller than or equal to An in order to force An to diverge. But we weren't always able to get these inequalities in exactly the right direction. And so that is very much what the limit comparison test is going to avoid. Okay, if you're still convinced that your series behave in the same way but you are unable to get the inequalities to work out, that's where the limit comparison test comes in. So the setup is very much the same. We have two series, AN and BN, both with positive terms. And this time, we're not going to be comparing AN to BN directly. Instead, what we're going to do is we're going to compare the two as a limit. Okay, we're going to do the limit as n goes to infinity of AN divided by BN. So in other words, what we want to know is what is going to happen as a ratio between the terms of AN and BN as n gets infinitely large. What happens sort of on the tail end of our series? And the conclusion is this: if that limit exists, if it's equal to some constant c, where c is just some real number and it's not equal to 0, then AN and BN are either both going to be convergent or they're both going to be divergent. In other words, what we end up getting is that AN and BN will have the same behavior. So they are either both convergent or both divergent. Now, that should actually sort of remind you of something, okay, and it should make sense when you think about it. So let's just sort of look at what's happening when we do this limit. What does it mean when this limit is equal to c? So in the past, we have talked about one very important rule when it comes to limits, and that limit rule is L'Hopital's rule. Okay, so we know that if we're doing the limit as, for example, x goes to infinity and I have e to the x divided by x, well, yes, both of these are going to be going to infinity, but that means it's an indeterminate form. What I am interested in knowing what this limit is actually going to give us, is I'm interested in what happens when I do the derivative of the numerator and the derivative of the denominator and compare them directly. So I get the derivative of x is 1 and the derivative of e to the x is e to the x. So literally, what L'Hopital's rule is saying to you is I'm going to compare not just the original functions, I'm going to compare their derivatives. I'm going to compare directly their rates of change. And what we're doing with the limit comparison test is going to ultimately give us the same sort of thing. We're going to be comparing the rates of change of AN and BN. In other words, I want to know, do they go to 0 together fast enough to converge, to be both convergent, or does one go to 0 faster than the other, in which case they may not have the same behavior? The idea being that if you get this limit as a constant, then they do both go to 0 at exactly the same speed, and so they have the same behavior. That's the idea behind the limit comparison test. It's very much the same idea behind what you've already seen with L'Hopital's rule. Now, we're not going to prove the limit comparison test, but I do want you to have some intuition about why it works. So now let's go and use the limit comparison test and see what happens when the regular comparison test fails and how we can use this on other series. So here we're looking at these two series and we want to know, do they converge or do they diverge? And this is actually the one that we looked at in the last video when we were doing the regular comparison test, and we said here we know AN is 1 over 2 to the n minus 1, and BN should therefore be 1 over 2 to the n, which is a convergent geometric series. So let's just sort of fill that in. It was a convergent geometric series. Fine. Now, we were convinced at the time that AN and BN should have the same behavior. However, when we looked at it, we said that an had a smaller denominator than bn, and so it was in fact a larger value than bn. And because bn was convergent and an was larger than a convergent series, the regular comparison test failed. So that is where we got the motivation to sort of look at the limit comparison test. Okay, and now we're going to use the limit comparison test to prove that still, even though the regular comparison test fails, an and bn should have the same behavior as a series. In other words, they should both be convergent. So let's just set up that limit. We're going to check what is the limit as n goes to infinity, and we are looking at here the limit of an divided by bn. Now, we're going to be doing a lot of these limits when we're doing limit comparison tests. So really, you could do the limit of an divided by bn. However, it's going to be a lot easier to always just set this up as an multiplied by the reciprocal of bn. So you'll see what I mean by that in a second. I have limit as n approaches infinity. An is 1 over 2 to the n minus 1. And the reciprocal of bn, if I take bn and I flip this, I take the reciprocal, then I'm just going to end up here multiplying by 2 to the power of n. And so that's nicer. Now I can just sort of put this together as one fraction. I have limit as n approaches infinity, 2 to the n divided by 2 to the n minus 1. And it should come as no surprise here what's actually happening. We end up with infinity in the numerator and infinity in the denominator. So we have an indeterminate form, but this is why just earlier we were talking about L'Hopital's rule. What I want to do now is compare these rates of growth. I want to compare which one actually goes to infinity faster. So let's compare directly their derivatives. And you may know where this is going. If I do the derivative of 2 to the n, I end up with 2 to the n times ln of 2. And I do the derivative of 2 to the n minus 1. And because the derivative of minus 1 is 0, I end up with just exactly the same derivative. I have 2 to the n ln 2 divided by 2 to the n ln 2. And before I even now do the limit, let's just simplify it. You end up getting that this is the limit as n approaches infinity of the number 1, and the limit of a constant is going to be a constant. So our limit here is 1. And now as soon as you're done doing these limits, you want to sort of stop for a second, check which test are we doing, what's the conclusion that we're interested in. We're doing here the limit comparison test. We compared an to bn directly, and we have a limit of 1. So is this a good thing or is this a bad thing? Well, for the limit comparison test, all that we needed is for this limit at the end to exist and for it not to be equal to 0. And so that is the case. We have a limit here that is not equal to 0, and so what we are now concluding, okay, and I'll write this out using the limit comparison test in a moment, but because this limit gave us a constant, because it gave us 1, it means that an and bn here are actually both approaching infinity with the same sort of rate of growth or rate of decay. They are both going to 0, in this case, at exactly the same speed. And so that's our conclusion, is that an and bn should have the same behavior. In other words, an should also be convergent by the limit comparison test. So here we have that an is also convergent by the limit comparison test. And so that's sort of the setup here. You might try to do the regular comparison test. The regular comparison test might fail you, and so you can go and try to do the limit comparison test if you're still convinced that an and bn might have the same behavior. So now let's go and look at just a second example. And here we're looking at something that looks initially a little bit more complicated. We're not going to be comparing this one to a geometric series for sure. We don't have any sort of exponential terms. Instead, we have polynomial terms like n squared and n to the 5. So here, let's look at it and determine which are going to be the important terms and which are going to not be important. So first off, in the numerator and the denominator, I'll look at them separately. Okay, and I'm going to have here a constant 5 and n to the power of 5. So this n to the power of 5 is going to dominate the 5, so I don't care about the 5. And in the numerator, the n squared is going to dominate the 3. So here, that's going to be what I use to decide on Bn. An is going to still be exactly this term that we started with, but Bn will be here sort of n squared is the dominant term in the numerator, and the square root of n to the power of 5 is the dominant term in the denominator. Now, you're probably asking yourself, what happened to this 2? What happened to the 2 on the n squared? Well, really nothing happened to it. I could put it there. Okay, we could leave the 2n squared there if you want. And actually, let's do that maybe for this example. I'll leave it as 2n squared over the square root of n to the power of 5. And then afterwards, we'll come back and we'll look at what would have happened if we had not included that 2. Would it have messed up the test, or would the test still have worked? So here, I have an and I have bn, but now let's sort of look at maybe doing first the regular comparison test. And the regular comparison test here is going to be a little bit tricky because when I look at an, it has a larger denominator, which would make me think that it's going to be a smaller number than bn. However, when I look at the numerator of an, the numerator of an is going to be larger than the numerator of bn. So directly comparing these two using the regular comparison test is definitely a little bit more complicated. It's not clear which direction the inequality is going to be, and so let's actually just try to use, instead of the comparison test, let's use the limit comparison test. So let's go and check what is the limit as n approaches infinity of an divided by bn. Okay, we want to see, do these two series go to 0 at the same speed? And actually, at the same time, let's not forget, we need to check, do we know if bn is going to be convergent or divergent? So here we end up getting that it's going to be 2 divided by, this was n to the power of 5 over 2. And so when I take into account this n squared in the numerator, I have just 2 divided by n to the 1/2. So what we are looking at here with bn is a p-series, and it is a p-series with p equal to 1/2, which is a small value of p, it's less than 1, which means that it doesn't go to 0 very quickly at all, and actually, therefore, it is going to be not convergent, it's going to be divergent. And so here, when I am now going to use the limit comparison test, I want to be able to conclude that an and bn have the same rate of decay, that they both go to 0 at the same speed, and so that they will both be divergent. So let's see if we can do that. We have limit as n approaches infinity. I have 2n squared plus 3 divided by square root of 5 plus n to the 5. That's my an. And now, rather than divide by bn, again, I'm going to multiply by the reciprocal of bn. So here, let's take bn and flip it. We end up with n to the power of 1/2 divided by 2 in the denominator. Okay? So what is this going to give us? Well, this is the limit as n approaches infinity. And I could sort of rewrite this. Now, if you think about it, we're still going to have the same problem we saw in the last one. We're still going to have to deal with that indeterminate form, infinity divided by infinity. And you could definitely look at this in terms of degree and say this in the denominator is degree 5 over 2. And in the numerator, it's also degree 5 over 2. And so, yes, they're both going to go to infinity at the same speed. We're going to have a limit here that's a ratio of their coefficients. But again, I want to go through the full explanation for the limit in case you're not familiar with how to do that. So what I can do is factor out the highest powers of n in the numerator and also in the denominator. So let's take out from the denominator n to the power of 5 over 2. And we're going to factor out that same exponent from the numerator. And this will work. It's going to be a little bit slower than what I just described, okay? But it's still effective, and we end up here with 5, or the square root of 5 over n to the power of 5 plus 1. And that's all multiplied by 2 still. And in the numerator, we will have here 2 plus 3 divided by n to the power of 5 over 2. Or actually not n to the power of 5 over 2, it'll be divided by n squared. Okay, so this is what we get if we factor out those terms, and now we want to clean this up and actually see what happens with our limit. So n to the 5 over 2 cancels in the numerator and the denominator. We also have that any term like this divided by a power of n is going to go to 0, and so really this limit is not so bad at all. We're going to get that it's equal to 2 in the numerator divided by the square root of 1 multiplied by 2 in the denominator. This limit is equal to 1. And so again, we stop for a second, think about the test that we're doing. We're doing the limit comparison test, so we are only interested in whether or not this limit exists. And if it exists, we want to know, is it equal to 0? It is not equal to 0. And so we now have that an and bn are going to be two series with the same behavior. So an is also going to be divergent by the limit comparison test. Okay, and so that's our second example here. Doing that limit, we get that they do have the same behavior. Now, I said before that we did not need to include this 2. In our bn, in our choice of bn, we didn't need to have 2n squared. So let's just go back sort of and take a look at what would have changed if we had chosen to not put that 2 in. Would the result still be the same? Would it still have worked out? So let's take out that 2, and that means that over here we're just going to have 1 divided by n to the 1/2. That means inside here nothing changes, but over here that 2 is going to be gone, and we end up with a 1. And then that means that this here is gone. We end up with a 1, but nothing else will change. And so all that ends up changing at the end is that this is a 1, and we end up with 2 divided by 1. And so our limit is going to be 2. It's not going to be 1. But that doesn't change anything because all we're doing is the limit comparison test. We don't care that the limit specifically be equal to 1. All that we care is that it's going to be a number that is not 0. Okay, and so when we're doing limit comparison test, it doesn't matter if you include the 2 there, if you include that scalar multiple, okay, that coefficient or not. It's not going to affect the behavior. It's not going to make it all of a sudden be convergent when it was previously divergent or vice versa. Okay, so you could include the 2 here or not. It's not going to change anything. So when using both the regular comparison test and the limit comparison test, what you need to develop is, yes, some intuition, but also some understanding about which terms matter when you're looking at these series. Okay, I can ignore these constant terms. Okay, because as n goes to infinity, this n to the power of 5, it's going to dominate the constant 5. And so in the next couple examples, it's going to get a little bit more complicated, okay, and we'll see and develop our intuition on what are good choices of Bn.